I teach at the Computational Linguistics department, and I'm also at the Center for Scientific Computing. So IWR is the German acronym for Center for Scientific Computing. And so the talk I give today is on linear learners. So why you all should know about linear learners already. So for those of you who know about it, I try to make the slides self-contained, so you can go back to the slides and use them as reference points, because I'm trying to do full derivations of algorithms and some little proofs end-to-end. And for those of you who don't know about machine learning at all, it will be a nice introduction, because all the classes that you will hear later on, they build upon this class in one way or another. All the techniques I will talk about today, like stochastic learning, regularization, nonlinear models, linear models, they will all come back again. So let's get started. So I want to start out with a model of the frog's perceptual system. So we can build a simple model of the frog's view of the world. And there has been a paper in the 50s or 60s that showed that the frog constructs his or her world by using 4 different detectors. So the frog can detect contrast, so is there a sharp boundary? He can detect convexity, is the object round or not? Then is the object moving, and how fast is the object moving? So that's the world of the frog, nothing more. No colors, no metaphysics, no laugh. It's just, this is it, yeah? And what the frog does is he detects objects and decides, can I eat them or not? This is basically the cognition of the frog. So the question is, can we model that? Can we build a model that does exactly what the frog does? And can we learn from data where we know those objects are edible by the frog and those objects are not edible? So we just collect data. What does the frog eat and what does he not eat? And then we learn a model that does the same. This is machine learning. So the model is built on data. So let's say we only look at 2 features, right? 2 detectors. One is convexity, so is it a round object or a big object? And the other one, speed. So basically what we have on the left-hand side is inedible objects that are small and slow, or large and slow, and edible objects, they are basically either they are small and move fast, or they are large and move slowly, right? So this is basically the idea behind these features. Now, how do we model this? So one way would be to define probabilities on the labels, edible, non-edible, based on the data, and then probabilities on the detectors that we call features, right? So what is the probability that we see a small object that is non-edible? That's the second line here. What's the probability that we have a fast-moving object that is non-edible? Or what's the probability of a slow object non-edible? Or do we have a slow object? Yeah, a slow object that is edible. So does anybody have an idea how we could compute these probabilities from the data we have here? So what would the probability of edible be, given these data, if that's all we have? Can we just count or do something? Yeah? And how? So you basically count up all labels, right, and take the fraction. 6 by 14 and 8 by 14 for the labels. Then for small objects that are non-edible, what would that be? So we just have to look at convexity, small, and get the fraction out of the non-edible ones. And we do that for all of them, right? For all features. So we get 6 out of 8. And for the edible, it's the same. We just take the fraction out of 6, right? So and what we did basically in this model, so we broke down the decisions into smaller parts that we then later on can build up together. So build up anew. So what we can basically do with this very simple model, we can now say something about data that we have not seen before. So we can say what is the probability of a medium-sized and medium-speed object. And if you look here, we have never seen this combination. We don't actually know from the data. We can't just memorize the data. We have never seen an object like that. So we have to build the probability of label plus or minus given convex medium and speed medium from our probabilities of features and labels. Yeah? So this is the core of machine learning. So you want to learn from data and then you want to apply to unseen data. Machine learning is not useful if you can just show that on your training data you do a good job. You can just memorize them. You have to learn to do a good job on unseen data. And this is a very simple model that does this job. So how do we do it? We just compute what the probabilities that we have learned before, the probability of inedible times convexity medium given inedible and speed medium given inedible. So we can look it up in the table and we get 0.027. And for the edible, we get 0.024. So our decision on the unseen data, our prediction is the object is inedible. All right. So the very same model has been used for a lot of different tasks in machine learning. So one of the tasks it has been used very frequently is text classification. So you have a text and the features are words in the text. And the labels are particular classes of texts, like a text about politics, a text about sports, and a text about this and that. The very same model. And the model that talks about text classification, well, some people think this is artificial intelligence. Nobody would say this is artificial intelligence, right? Because we are just talking about the frog's perceptual system. But it's the same thing. We are not more intelligent than the frog. We also construct our world by setting up a particular set of features and combining them and learning probabilities. So this whole artificial intelligence, I don't know. You just, I think it's better to stay with the term machine learning, right? We can apply to any data, natural language data, biological data, finance data, same thing all over. Okay, so my view on machine learning is a frog's world. What we do is we build models based on feature representations, similar to the frog, who builds his world or constructs his world by a four-dimensional vector of detection operations. We have a little bit more detection operations, but in principle, we are just animals like the frog, right? So there's no principal difference. And then what machine learning does, based on these feature representations, we learn parameter weights by optimizing a model. So this is the probabilities that we learned. We have to learn that from data, and then we want to apply it to unseen data. So the model I just showed is called naive Bayes. So we'll go into more detail for this model, and I will do the complete derivation of how you arrive at these probability estimates. It's a linear model. That's why this whole class is called linear learners, and the parameters are optimized by convex optimization. So the class could just as well be called convex models. Yes. So I make the difference between learners and models. So the model is how we combine the features, how we weight the features. That's a linear model. And then you can optimize the weights by convex optimization. And the nice thing is, at the end of the class, I will show you how you can use a nonlinear model that is more powerful and still optimize it by convex optimization. This is something that's different from what you will see at the end of next week, where you have nonlinear models that cannot be optimized by convex optimization. So neural networks they can do the same thing as we can do, but you have to make some, you have to step from convex to non-convex optimization. Okay, so I will give some examples of feature representations. Then I will define what the linear model is, and then I will give you a self-contained overview over 4 linear models that can be optimized by convex optimization: naive Bayes, logistic regression, the perceptron, and support vector machines. And the classes that come later, like structure prediction or the neural network class, they will build on the perceptron, for example, or they will build on our implicit. So basically, I'm not talking about binary classification here, which is a special case, and most textbooks from the 90s and 80s always talked only about binary classifications. I will talk about multi-class classification right from the start, because this will prepare you for the structural prediction classes, and then some techniques to refine the convex optimization to get the models make more powerful models and more efficient learners. Okay. So our definition of inputs and outputs is, so we have pairs of inputs like documents or sentences for natural language processing, and our outputs you can think of them as structured outputs or as classes, and more than one class or more than 2 classes, like a document class, like politics, sports, finance. A translation, if you have a machine translation model, the input is an English sentence, the output is a set of German translations. Or parsers, you have an exponentially many parse trees in the size of the input sentence. And so we always have, the data are given as pairs, right? So we do supervised learning. So all the other facets of learning, reinforcement learning, unsupervised learning, semi-supervised learning, they can build up on this setup. So feature representation, that's the most important thing to understand to map this frog model onto our formal framework. So we have a joint feature representation. So by joint feature representation, what I mean is the features are defined by looking at input and output jointly. So for example, feature representation, as I just gave it before, like translations. For translations, you always have to look at the source and the target at the same time, right? Otherwise, it doesn't make a lot of sense to have a feature representation just on inputs. You want to know what is the translation a translation of, right? And the ranges of the feature vectors can be counts or categorical, or they can be binary. So for example, you can, even if you have real valued features, you can say if they are in the range from 10 to 100 in this bin, then I say yes or no. So that's a common way of having features. Or you just have binary features, indicator features, or you have real valued continuous features, which are now common in neural networks, word embeddings. So the notation will be the feature vectors will be boldface. I hope you can see it whenever we use it. And the index, so the subscript, will be the chase value of the feature vector. So an example, again, is this would be an example from text classification. The label is financial, and the feature is, do I see the word interest? So, and you would guess that this feature should receive a positive rate, right? So interest is a positive indicator of the label financial. Then another example would be, again, text classification. The label is scientific text, and this time it's not a binary feature, it's the percentage of words that contain punctuation, which would be a good indicator for scientific texts. Then, if we do part-of-speech tagging, for example, you could say, do I see the word bank and the label verb? Or do I see the word bank and the label noun? This is a feature to indicate that the label we want to assign is verb or noun. Then for translation, a feature map would be, so you see you have source and target here, yatil and are there. So one is in the source, one is in the target. That's one feature. Do I see that the phrase translation pair yatil and are there, or do I rather prefer the phrase translation pair yatil and are there any? So the second one is the one you actually get. So I took this from an actual model, and what you would actually prefer is this one, right? For anybody who speaks French, but that's how it is. An example from parsing would be, this is our input, the dog chased the cat, and this is one output, a parse tree, and the feature representation could be, you just, from a context tree, parse tree, you just count the occurrences of rules, right? S to MP, VP, and so on. So each rule gets a count. All right. So how do we make a model now that we have the features? So I showed you features for natural language processing. Before we had features for the frog's perceptual world. The linear models, what they do is, the model we want to learn is a linear combination of features and weights. And since we have more than one class, so what we want to do is we want to find the model when we do prediction that gives us the maximum valued label under this linear combination, so a linear discriminant function. So basically, when we want to do prediction, we want to do multi-class classification. So the model we learn, we directly use to do prediction. So what we want to do is we want to predict the label that has been seen in the training data, and we hope that the label that we have learned from the training data is the correct label on unseen data. Yeah? So we do an argmax over this linear combination. And binary classification, as you can see, is just a special case of this, right? You have two classes. So the model looks like a quite simple model, but those models can be quite complex because the feature representations can be large and they can be sparse, and it might be very difficult if you have an exponential space of outputs, like for machine translation. For each source, you have exponentially many translations to search this space to do this argmax. So this is all, you will learn about all of this in the later classes. About the sequence model class will teach you dynamic programming techniques to do this argmax efficiently. The structural prediction class will tell you about same things. Yeah. So structural prediction means that you not just have classes, but the classes have structure, like translation. Can you use this structure to maybe do more efficient inference, or build a better model? Yeah. So this is the picture everybody has seen in textbooks from the 80s and 90s, binary classification. So a linear model can be seen as a model that builds a hyperplane in n-dimensional space between positive and negative instances. So in two-dimensional space, that's a line. And for multi-class classification, it's very similar. You just have to build a partition of your space, and you build several lines. Yeah, you differentiate the plus labels from all the others, and then the zero labels, and then minus labels from all the others. But it can be built up as a hyperplane classification problem as well. Okay, so the model was this. Now the question is, how do we learn the weights? And this is now how machine learning becomes actually a special instance of optimization. So everybody, mathematician, statistician, computer scientist who works on optimization is, well, a better machine learner than we all are, because we just go to their works and try to understand it and adapt it to our problems, right? But all the ideas and the techniques, they come from the optimization theory. So we just apply optimization to our models, and the best researchers in our field, they make smart adaptations of known optimization theory to our problems, and then maybe develop something new. But it's most of the stuff I'm talking about today, this is well known in optimization theory. It's just convex optimization, unconstrained, constrained, and so on. But what's nice about our area is some some optimization theory guys, they come into our field because we have interesting data, challenging data that force them to think about more efficient and faster converging algorithms, because these data sets that have been around in machine learning for a long time, they are, from our perspective, quite simple. It's mostly really just multi-class classification or even binary classification. And our sequence models are more challenging. Okay, but how do we learn the weights? Convex optimization for supervised learning. So what we assume is, we assume that our data, the inputs and outputs, are independently and identically distributed, which is a lie right from the start, because in natural language processing, the data are never independently distributed. Sentences in a running text that you want to translate are not independent of each other, but you treat them, every sentence is independent from each other. Or words in a sentence, if you do part of speech tagging, they are not independent, but anyway, it works. Then, so what we do is we set up an objective function on the training set, and then we try to use optimization theory to optimize our objective function under the parameterization, under our linear model. So for example, we have an objective function called L, defined on the training data, and our weight vector, and we either maximize or minimize minus L. So ideally, the objective functions are decomposable over training examples. So that means for each training example, we can compute a loss or an objective, and then we can sum up the losses or objective values for the training example. So we can do it training example by training example. This will enable us to do the technique that I will talk about later, online learning or stochastic learning. So you do it example by example, more efficient, nicer, doesn't use as much memory. And so this is one of the main assumptions I'm making here, decomposable loss functions. So an example would be a very simple loss function, the 0-1 loss. 0-1 loss says the prediction I'm making, so the argmax over the linear model, equals my the label on the training set, then I have loss 0, otherwise I have loss 1. And I can do that on every single training example, and then the loss over the full training set is the number of times I did a misclassification. Okay. So in order to use convex optimization, we have to make the assumption that our loss functions or objective functions are convex. So the definition of convexity is here. So what it means is that the function value lies always below the line that connects any 2 points on the graph. So what this means is, as you can see, that there is only one minimum, one global minimum of this function, right? Because the function value is always below any 2 points that you can find on the graph of the function. And what convex optimization, the techniques we are using, does it uses the gradient of the convex function to find this global minimum. And the gradient is the vector of partial derivatives. And what the gradient tells you, it points in the direction of the fastest increase of the function. So this is the direction of the fastest increase, so up here. So what you do is, if you want to minimize a convex function, you go in the negative direction of the gradient. So the negative direction of the gradient will always lead you towards the global minimum. So this is the key idea here. So we assume convex functions, we use the gradient information, and question, can we use this function here as our objective function if we want to do convex optimization? Is this a convex function? Would be nice if we could use this here, right? But this is not convex. This is piecewise linear, right? It's 0, 1, 0, 1. This is definitely not a function that we can use. So all the objective functions that we will use in our models, they are different convex approximations on the multiclass version of the 0-1 loss function. So the key idea, so this has been a research topic for 20 years or longer. Now the field shifted more towards making the models richer and more interesting, and not basically the objective functions. The objective functions are not of that much of interest anymore. I think there has been a lot of work on that already. But it has been, so I will show you a slide later on where you can see what the different approximations, convex upper bounds on the 0-1 loss functions are. And each single objective function corresponds to an algorithm. So my way of understanding machine learning is you have a problem, you identify the problem that you actually want to solve, like this binary classification or a multiclass classification loss, and then on top of it you build an objective function that you can handle, where you have techniques to solve it, and you take the derivative of the objective function and find an algorithm that is efficient. So you always start from the problem, formalizing the problem, and then deriving the algorithm. You never start from the algorithm and then later on try to figure out if the algorithm, what it does, what it actually optimizes. This has been done, but sometimes people got lucky and found out actually my algorithm optimizes a useful objective function, but no, it makes more sense to go the other way. Okay, so talked about convexity, gradients, and convex optimization now. Is the problem of finding a point that minimizes the objective by following the opposite direction of the gradient, and you arrive at the point, at the global minimum, at the point where the gradient is 0, right? You can see the global minimum here. The gradient is just a horizontal line. This is where you want to arrive at. And all the algorithms that I will talk about, they are just instances of setting up an objective, taking the derivatives, having an algorithm, and in the best case, showing that it not only works on the training data, optimizes, finds the global minimum on the training data, but also does something useful on the test data. So this is what statistical learning theory is about, which is also, when machine learning covers many, many different topics, like artificial intelligence. If you talk about things that are different from the frog, right, it's called intelligent, even if it's just text classification. Or statistical learning theory is going beyond what optimization theory does, namely not just talking about the training set, but talking about the test set. Okay, so naive Bayes. So this is the algorithm that we use for the frog. So the decision model that we build is we want to find the probability of the label given input that maximizes the product of label and input given label. So this is just Bayes' rule, as you can see here. And since the input is fixed, we can just ignore it. It's the same. And the nice thing about naive Bayes, which can be useful for many applications, it's a generative model. Since what you actually learn is a joint probability. So you're not learning directly the probability of the label given the input. You're learning the probability of label and input. So you could turn around the model and generate. So you could turn around and generate labels, which you can't do in a model like that. Or you can generate inputs because you have the joint probability. But sometimes, as you will see, the next model, the logistic regression model, takes the point of view of Occam's razor. So you should only optimize what you actually want to see. And if you actually only are interested in classification, then you just optimize the conditional probability and not the joint probability. But naive Bayes optimizes the joint. So why is it called naive Bayes? So Bayes because of Bayes' rule, and naive because we are making an independence assumption of the features. So actually if you would just unfold this probability of all features given label, you would always have the history of the features in your conditioning part. And what naive Bayes is, it takes the probability of the features given the label and forgets about all the history. All the features are considered independent. This makes it very easy to optimize this model. So the joint probability that we want to learn is the probability of the label and the product of the features given the label. So most models in natural language processing were of this type in the 1990s. So the first book on statistical learning by Eugene Charniak, I don't know if anybody knows this book anymore. It's a very small, nice book. It talked about language models, parsing, text classification. All the models were of this type. Because what these type of models allow you is to do inference by just counting from the training data. So you don't have to have iterative algorithms. And the reason that's the reason why people make this independency assumption, because then you can do this count frequency, relative frequency estimator. But it's not immediately clear why making this independency assumption allows you to do this relative frequency estimator. It will become clear if we do the full derivation. This is what we will do now. So we parameterize our model. So it's the probabilities of the labels, probability of the features. And what we optimize, our objective is the maximum likelihood of the training data. So what it just means is we instantiate these probability models for all of our training data pairs, all xt, yt in our training set. So it's the product of these probabilities. Okay, and the independency assumption that we made before gives us a nice property in optimization, which is called a closed form solution. So that means some parameters that we would normally, where we would normally have to use iterative algorithms to estimate them, they can be calculated in a closed form, in an explicit form. And so in the end, we end up with an estimate that doesn't need to optimize any parameters that we can't get from counts from the training data. And this is only possible since we have this independency assumption. So in the end, what we will have is the estimate for the label probability is the number of counts that we have seen this label in the training data divided by the size of the training set. And for each feature, the estimator is how often did we see this feature with this certain label divided by these labels. That's what we did in the very beginning, right? Remember what we did for the frog? We just did relative frequencies of label counts and relative frequencies of feature counts. And how can we derive this? So in the Charniak book, for example, since it's really funny. So the whole book builds upon these models, but nowhere in the book is a derivation of this relative frequency estimator. It just falls from the sky. So but here you have it. We will derive the maximum likelihood estimator here. You can go back to these slides for reference. So what we want to find is we want to maximize this objective function with respect to p. And p is these parameters here. So we just rewrite it a little bit. Since we are taking the argmax, we can just take the log product. So then we have a sum of log probabilities. And we can, the argmax of this term, of this sum, is the argmax of the first sum and the argmax of the second sum. And you have to be careful here. Since we have a probability model, we have constraints. So the constraints are the probability constraints that say that the label probabilities have sum up to 1 and the feature probabilities given a label have to sum up to 1. So in terms of optimization theory, what we have to do is constraint optimization. So I can't give an introduction to constraint optimization now. We'll just have to swallow it. What we reformalize the problem a little bit more by looking at those two terms and seeing that they both have the same form. Namely, we have a sum over events, count of event, log probability of event, and constraints. Yeah? And the event is either a label instance or a feature instance. And for this form of objective, now we do constraint optimization. And constraint optimization means for each constraint you have to introduce a Lagrange multiplier. And this is the standard form of the constraint. So you set the constraint to 0. And setting it to 0 means pulling the 1 to the other side, minus 1. And now we have to solve this problem. We have to solve it for p and lambda. So and what I mean by closed form solution is if you have unconstrained optimization, you're fine, right? You can just solve for p and get a form, and hopefully it's a closed form, you're done. But here you have p and lambda, and closed form here means that the lambda can be calculated explicitly in terms of the other parameters. So you don't have to optimize for lambda separately. So there are a lot of constraint optimization problems where you have to do that. But for this simple model that we have, we don't have to do it. And this is why it was so popular in natural language processing in the beginning, in the years where people use probabilistic context-free grammars and n-gram language models and naive Bayes. So this was the 1990s. But it's still a nice and simple model. So the derivative of this Lagrangian with respect to p is count divided by p minus lambda. Can you see that? So the derivative of log p is 1 over p. This is how this, where this comes from. And this is just the derivative is 1 here. So we have lambda times 1. Then setting this derivative to 0 because we want to find the point where the derivative is 0. This is where the global minimum lies. We get this form. And then the closed form solution now means we can calculate lambda explicitly by using the probability constraint. And then we see that lambda is just can be expressed as the sum over counts of the events. So what we get in the end is our probability estimate is the count of the event divided by all other counts, so the normalized count or the relative frequency. And this is the whole derivation. So you have to know about how Lagrange multipliers work, and then you can see that having this objective, you actually arrive at this here. It does not fall from the sky, and you have to make some assumptions in order to get that. If you violate these assumptions, if you don't have this independency assumption, then you will see no closed form. You will have to use other algorithms. Okay, so here again, our estimates. Then I want to show you why is naive Bayes a linear model. We had all these products. Well, if you just take the parameters as log probabilities and you define features as instantiations of feature values, then you will see that what you get by starting from this model, just reformulating it a little bit, log probabilities, and seeing how often do you see this event, then you have this linear model where you have W and phi just counts, do I see this label, do I see this feature, and W is the log probability. So it's a linear model. And it's a generative model, because the next model is a discriminative model. So what I said before, generative model means we model the joint distribution of inputs and outputs. And this is, for the longest time, this was the only way statisticians deemed estimation proper. They always wanted to have models that were generative models, models that you can turn around. So basically, even if you have discrete data for a statistician, you want to do density estimation, and you want to have a model of the probability density that produced the data. And for discrete models, it means you want to have a model of the generative process that produced this data, these labels and inputs. But Occam's razor, now that we do machine learning and all we care about is not simulation or turning a model around, all we care about is we have a test set or an application and we want to do good predictions, and predictions means conditional probability, probability of label given inputs. So Occam's razor says among competing hypotheses, the one with the fewest assumptions should be selected. And the one with the fewest assumptions is the one that just gives you probability of label given input. So what we should set up is an objective that models this conditional probability directly. And logistic regression, the next model, is one of those models. Or the models that we will see later. They are even more farther apart from density estimation, since what they do is they minimize the classification error directly. They are not even bothering about probabilities anymore. All right. So this was naive Bayes. Next on, logistic regression. So logistic regression is also known under many, many different names. So it's in our community, it has been named or has been known as the maximum entropy model. I will give a short explanation why this would be also a proper name. Then another name is, so in the image or in the vision community, it has been known as Markov random fields or Gibbs models. So they're all the same type of models. It's a normalized linear model. And logistic regression is just the standard term that the machine learners have coined for that. So regression is a type of machine learning problem where you don't want to predict a multi-class label, but you want to predict a continuous variable. You want to predict the value of something, like like a severity score, if you do prediction in medical data, or I don't know. So it's a funny name for, since we use it for multi-class classification, it's called logistic regression, but this is the standard term that is now run under. It used to be called the maximum entropy model in our community. So, but what it is it's just the linear model we had before taken up, so taking the exponent of this and normalized. And the normalization just ensures that you have a proper probability distribution. And so another name is called the log linear model, because if you take the log of this, then you see it's a linear model, right? Log of E, and you get the linear model back. Yeah. So that's what I just said, the log linear model. If you look at the argmax, the prediction model, the prediction problem, you can forget about the normalization and you directly get the linear model. Okay, so learning the weights for this model, so it looks very similar to the naive Bayes model before, but since we have this normalization constant, we can't get a closed form solution anymore, because this normalization constant also contains the parameters, right? So the normalization constant was defined as the sum over all labels of this exponentiated linear model. And this introduces problems in optimizations. You will have dependencies of the parameters, and you can't solve to get a closed form solution. So what you have to use iterative algorithms. So what we have to do first is, now that we have the model is motivated by optimizing the conditional probability directly. We again do maximum likelihood estimation for this model. It's the probability of labels given inputs, or same as the log probability, sum of log probabilities. Then if we look at the objective, we see the objective is concave, so minus objective is convex. And we have to use numerical techniques to do that. So in the 1990s, there was a lot of work done on finding efficient estimators for these log linear models. So there have been a lot of specialized algorithm, iterative scaling, improved iterative scaling, generalized iterative scaling, iterative proportional fitting, whatever. And in the end, people found out just going to the optimization theory literature and taking a standard gradient ascent algorithm works just as fine, or even better, because you can use all the knowledge that the optimization community has built up on how to speed up convergence, how to make sure that you do good on unseen data, and so on. You can just take over all this knowledge if you use their algorithms. So the algorithm I will talk about today for optimizing this logistic regression problem is a simple gradient ascent algorithm. So what it does is, if you have this concave function, so it takes a step in the direction of the gradient to find the global maximum. Or if we turn around everything, then we do minimization. So the algorithm looks like this. We set our parameters to an all-zero vector, And then until convergence, what we do is we update our weight vector by going in the a certain step size, a positive step size, small or large, increasing, decreasing, constant, whatever. So we have to learn this from optimization theory, what's best, in the direction of the gradient. So the gradient for our objective is, as I said, the vector of partial derivatives. So what we have to do now in order to understand what's going on, again, we have to set up an objective and do optimization, find the derivative, then we can set up our algorithm by just plugging in the derivative here. And we are done. And we know everything, well, not everything, but from optimization theoretic point of view, we know everything about the algorithm. Okay, gradient descent is the same, minimizing the objective, so we go in the negative direction of our gradient. Okay, so now I will give a little bit lengthy derivation. Unfortunately, it's lengthy, but it's good for you to have a look at this, because in most papers nowadays, if anybody uses a linear model at all, most people don't use linear models, but some people still do, they just give you the end result. This is the derivative. And it's nice to go through the steps and see how you get there. It's not that hard. You have to use a few rules of derivation, but it's a very enlightening derivative that you get for the logistic regression. So the objective is the log conditional probability. We define it by this Gibbs model, log linear model, maximum entropy model, logistic regression model. And what we have to use for the derivations is the log rule, the exponent rule, the sum rule, and the product rule for derivatives. Yeah? So they are easy, 1 over, this stays the same, the sum you can pull out, and here you have this funny term of taking the derivative of the numerator and denominator and then squaring. Okay. So I'm just giving the definition again, and I'm using the log rule. So the log rule takes 1 off my term and multiplies by this. So next step, I'm doing now what I had on the right-hand side before, right? I'm left with this. So for this, what I'm doing is I'm taking the product rule, yeah? Or, yeah. So it's the denominator times the derivative of the numerator, then the numerator times the derivative of the denominator, this here squared. Then I'm taking the derivative of this term here. You can see that's easy, yeah. It's e up to the sum, stays the same, and the derivative of the linear model is just the feature vector. Then I'm pulling out common terms here. So I'm pulling out the denominator and e up to the sum of the linear model. I'm ending up with this term. And then I'm taking the derivative of the normalization constant, which is given down here. And the derivative of the normalization constant is, so this is the definition. So I'm just using the exponent rule again, so the exponent stays, and then I'm taking the derivative of the inner, namely the linear model, and I'm plugging it in here. So, and we are not done yet. So what I had before is the derivative of this term of, on the right-hand side was this. Then the likelihood was defined as the right-hand side term and the left-hand side term. So we have taken the derivative of the right-hand side term, the left-hand side term before, and now we just have to do a few shufflings, so pulling out yeah, where is it? Yeah, so this is also easy. Yeah, this is just taking this derivative here, and then we are yeah, E C. Yeah, I don't know how to. We're just going step by step, doing reformulations, ending up with this term here. This term here is, it's very simple what it says, and this is why this derivative is instructive. So what it says is you are counting in your training data all the instances of the features for each feature vector, and on the other hand, you have the expectation of this feature vector under your model. So you're summing up the probabilities of your feature vector under your model. So what this is here again, it can be seen as a constraint that at the optimum of your log linear model, of your logistic regression model, the counts of your features in your training data have to be equal to the expected counts under your model. Because what you want to do is you want to set this derivative to 0, right? At the optimum, this term is equal to this term. So what you have is you have a constraint that says, build a model, find parameters that tell you under my model the expected feature counts are the same as the feature counts in my training data. And it's a very simple formulation, and the reason why the model is called maximum entropy model is exactly for this reason, because maximum entropy starts from setting up exactly these constraints. So the constraints under maximum entropy model are the constraints that say, under my model, the feature counts have to be the same as the feature counts in my training data. And if you maximize the entropy, then you find a uniform distribution that respects your constraints and does nothing else. So the maximum entropy model is one way of motivating this logistic regression model. So the form of the logistic regression model, so all the weights that we have, they can be seen as Lagrange multipliers that come from our constraints. So for every constraint that says feature expectation under the model has to be the same as feature expectation in the training data, we set up a constraint, and then in the end we end up with the logistic regression model. And another way to look at it is if you start from the logistic regression model, then you see at the optimum you're satisfying this maximum entropy constraints. So this is where the name comes from. But it's not really necessary to understand the model. You can just start from the Gibbs model, log linear model, and say, this is a model that I like, that makes sense. I want to have a probability model. I want to have a linear model. And then you go from it and you forget about the maximum entropy formalization. But it's also nice to know there would be a way to motivate my model. All right. OK. So now we had naive Bayes, which was a joint probability for a linear model. Logistic regression used the very same model and optimized the conditional probability directly. So the difference between the two was the first allowed relative frequency estimators. So it's not something that we choose. It falls out from the model. By taking the derivative of this model, of the likelihood under this model, we find that the relative frequency estimator is what we can use to find the optimal parameters. For the logistic regression model, where we do something smarter, seemingly, by doing the conditional probability estimation, we have to use iterative optimization algorithms like gradient ascent. Yeah? So we can't just count. So we have to implement an algorithm that maybe runs for a week or so until it converges and finds the parameters. So nothing comes for free. If you change your model, then you have to use a different algorithm. And it falls out from just taking the derivative, and you see this is the derivative. It's not a closed form solution, so I have to find an algorithm that solves for these parameters. And gradient ascent is one simple algorithm that does it. Because if you just go in the negative direction of your gradient at every step, you can imagine for a convex function, at some point you will end up at the minimum, where the gradient is 0. This is the only point where the gradient is 0. That's the point you have to find, but it can take a while. Okay, the perceptron is also a linear model. It's actually one of the very first linear models that has been around. And it was motivated in a completely different way. So people who invented the perceptron, they actually started from the algorithmic point of view. So they had an idea. This is how I think an algorithm should work. This is how I think what it should do. And they gave a proof of convergence. The algorithm actually does what I'm thinking it should do. And only later people found out, okay, we can set up the perceptron algorithm as a standard machine learning algorithm that takes an objective, takes the derivative, and does gradient ascent. So that was developed later. But what is really nice about the perceptron algorithm is it's the basis of neural networks on the one hand, and on the other hand, this proof technique that was developed by Novikov and Bloch in the 50s, it's so general and so nice, you can even apply to non-convex models. So it's a really nice way of doing proofs. It's different to taking the objective and showing you are arriving at the minimum of the objective. You are not talking about objectives at all. So I will go through the proof so that you see how different it is from what we did before. What we did before is just we have an objective, we say, or we prove it's convex, and then following the negative direction of the gradient until the gradient is 0 will lead to the minimum. Yeah, that's basically the proof. It's very easy to give. I didn't give the proof, but it's easy to understand. And for the perceptron, the proof is totally different. And it's so nice and general that it can be used, yeah, for non-convex models as well. Okay, that's the algorithm. The algorithm basically so this is the perceptron for multi-class classification. So it's not the original perceptron from the 1960s, but it's a slight modification. What we do is we go for n rounds over our training data. So each round is called, or epoch, going over the training data once is called an epoch. Then the t's are the training data. Then what we do is, for each training data, we do a prediction. So we do our argmax. And then we check, did we do it right or wrong? If we did it right, then what we do is nothing. We can continue to the next example. If we did it wrong, then what we do is we update our weight vector by adding the feature representation of the positive example, so of the gold standard label, and subtracting the feature representation of the example that we wrongly predicted. So this was the idea of the perceptron algorithm. So what I'm doing is I'm following the training data. I'm checking if I'm doing mistakes or not, and I'm moving my weight vector to follow the positive examples, right? So if I'm doing a mistake, then I'm changing my weight vector to look more like the training data and less like the wrongly predicted example. And as you can imagine, this algorithm, it works, but it might take a while, because if the training data are complex, then it will wiggle around a long time and be distracted and so on. And so this is the next algorithm that we will learn, that you are not wiggling around too much, and another problem is it will exactly mirror the training data, right? Because all it does is just running after the training examples. It's not taking care as algorithm about unseen data. It just, as the algorithms we have seen before, it's just taking care of making sure I get my training data right. And machine learning algorithms, as we saw, they should also do good on unseen data. And this is the support vector machine is one algorithm that makes sure that you do good on unseen data, and there are other techniques to do that. But that's a very simple algorithm, and we can give a proof without talking about objectives that it does what it should do, namely making sure that on the training data, after a certain round, a number of iterations, I'm not making any errors anymore, which is what we want. And it's the basis of more complex models. By stacking perceptrons, you get to the multi-layer perceptron, which you will learn later on, which is the basis of neural networks. But it all started here. And why is it called perceptron? Because it was thought as a simple neural network when they started out doing this. So if you read the papers, the original papers, it's all full of blah blah about neurons and the brain and so on. And yeah, there were follow-up papers that showed that the model is not expressive enough. There are things human can do that this model can't do, and so okay, then this is where neural networks really were invented, by moving the single layer perceptron to the multi-layer perceptron, where you could solve some nonlinear problems. So that's basically, but this is where it started. Okay, so the proof for the perceptron algorithm is based on this definition of separability and margin. So separability means we have to assume, so this is when the proof works, the simplest version of the proof. You can give a proof for other versions as well, but the proof I show now is if you have training data that are separable with a margin greater than 0. So margin greater than 0 means it's always possible to find a weight vector with norm 1 such that, so the weight vector is now it's called U, such that the weight that you assign to the positive example, so to the correct training example, to the gold standard example, is larger than any other example by a margin of gamma that's greater than 0. So you can separate the correct example from all the others by a margin greater than 0. Yeah? So a margin of 0 would be, okay, I can just do it right, but a margin greater than 0 means I'm doing it right, but I have a little bit of a confidence that I'm doing it right. Yeah? Okay. So under this assumption, we can show that the mistakes that the perceptron makes during training is bounded by r squared divided by gamma squared. So there's many ways to interpret this. So one way of interpreting this is the number of mistakes during training is bounded. So it means at some point we won't make any mistakes anymore, right? That's one important point, right? Bounded means it's not infinite. So if you train long enough, no more error, fine. Then another interpretation is the size of the error is defined by r squared. So the larger r squared, the larger the error. And r squared is just the size of our feature vector. So why would this make sense? So if you have a large feature vector, like millions of features, then the error might become larger. Why would that be? So the point is what the perceptron algorithm does, and this is also different to the algorithms before. The perceptron algorithm, it makes always a prediction on the next example, right? So the next example that it makes a prediction on is actually unseen to the perceptron. So this is why the perceptron is an online learning algorithm. So unseen means I'm going through the data, and initially the perceptron was invented for, or the online learning algorithms were invented for infinite sequences of data. So every time you make a prediction, the data you look at is unseen to you. So it's basically making a prediction on test data and then shifting your parameter vectors. So if your feature vector is huge, then it might be not intuitive, but you might have learned too much on the history, or you might have adjusted too much to the data you have seen before, and you're not doing a very good job on the next example. So it's basically having a too rich model is not a really good idea. So you should have a model that, again, Occam's razor, that only knows what it's supposed to know, only the most important features, not everything, all and everything, right? This is why the number of mistakes is negatively affected by the size of the weight vector, or of the feature vector. And gamma squared, so if gamma is larger, so if the training data is easier, so if they are separable by a large margin, so if it's really easy to say this is the good ones and this is the bad ones and this is the other ones, then the problem is also easier, yeah? Okay, but now let's prove it. This is again the algorithm, and what we do is we derive a lower bound on our weights, and we derive an upper bound on our weights. So the weights that we end up after learning, and then it's what's nice about the algorithm, we can take the ingredients that we used in bounding from below and above, namely this R squared and the gamma squared, and bound the number of mistakes. So what we do is, by calculating the lower bounds, so we assume that the weights W at step k minus 1 are the weights before we make the case error. So making an error means that we are not predicting the right label. Then under this assumption that we are making an error, we can use assumption number 2. So this is our basic assumption, that the training data are separable, and plug it in here. Yeah, this is just our update. We multiply the left-hand side and the right-hand side by our vector u. And then we see for this here we can make use of our assumption number 2, namely that all the training data are separable by a margin greater or equal to gamma. So that means we can replace this here by gamma. So what we now have is u times w at step k is greater or equal than u times w at step k minus 1 plus gamma. Then we can do an induction on k. And the induction on k tells us that u times w at step k is greater or equal than k times gamma. Yeah, doing an induction on these steps here, and assuming that we start from the zero weight vector. Then we are making use, so this is always with proofs like that, people make use of some laws of, yeah. There's no full list. I don't know a textbook that gives you a full list of all these laws of geometry that you can use here. But one of the laws that is used very frequently is the law of cosines, and the law of cosines tells you that you can, every dot product can be upper bounded by the product of the norms of the components, and we apply this to our term here. So this u times w is now lower bounded by norm of u times the norm of w, and since we said that the length of u is 1, what we have is our lower bound. Namely, the norm of our weight vector is greater or equal to k times gamma. So as a standalone result, what it means is for every step that we do, we are learning a weight vector of length greater or equal times gamma. For the k step, it's k times gamma. Yeah? So we are running after the training examples and assuming that the training examples are separable by margin gamma. Then to do an upper bound, so you see the result here already, we can get a result that tells us the squared norm is less than or equal to k times r squared. How do we get there? So what we do is we just unfold the square here. So it's w squared plus 2 times. So we are using again our update, right? And for the update we are using the rule of squares, right? X squared times 2 of xy times y squared. This is y squared, x squared, and 2 times xy. And for this term here, we can see that this, by assumption, is upper bounded by r. So the norm of, now this here, r squared. This was our assumption on the size of the weight vector. And since we are making a mistake, we know that this is less than or equal to 0, so that we can drop it in our lower bound or in our upper bound here. And so what we end up is we get the norm of the weight vector squared is less than or equal to k times r squared. So if you look into any paper for the binary classification or the voter perceptron or the multi-class classification perceptron, you won't find a proof that is any more detailed than this. So you will, this is it. Yeah? If you want to understand what the perceptron algorithm, how it's proved, this is it. All you have to know is you have to know the law of cosines and you have to know how to do induction. So, but how do we use this? So we have the lower bound, we have the upper bound. And from the lower bound and the upper bound, we can calculate and solve for k, which is what we are interested in here. And we get k is less than or equal than r squared divided by gamma squared. So how do we do that? So since this is less than or equal than k r squared, we can forget about the stuff in the middle. And we have k squared gamma squared is less than or equal than k r squared, and then we can solve for k. And we get the result. Yeah? The number of errors is bounded, and it's bounded by the size of the feature representation, and it becomes smaller by the size of the margin. And so in the whole proof, we never made an assumption about convexity. And I never mentioned convexity. I never mentioned any objective. We just went through the steps and we proved this. So this is why it's a very nice and general proof. You can apply it to any algorithm if it satisfies certain conditions. Yeah? Okay, so later on we will see how the perceptron actually can be interpreted as an algorithm that optimizes a certain objective. It's quite easy to see. We will give the objective later on. Now what I want to point out again is it's an online learning algorithm, and this is one of the differences to the algorithms before. So when learning, the perceptron always looks at the next examples that it doesn't know at this time. Right? It makes a prediction for the next example and then learns from its own predictions. It's not like the naive Bayes algorithm, which just counts from the training data. It never makes a prediction while training. And online means I'm doing my updates on each example separately. I'm looking at an example, making a prediction, doing an update, and then the next one. So in online, so this comes from the idea that you have a sequence of data that is coming in online, and you have to learn online while the data is coming in. You don't have a finite sequence of data, but you can as well use it on a finite sequence of data, right, or a finite set of data by looping over the data. And a good idea is to reshuffle the data each time you loop over the data. Okay. So another point I want to make, because it's easy to make, the perceptron is mostly used as the average perceptron. So averaging means that you're not using the weight vector that you have in the end after doing your n epochs over your t training data, but you are just taking the average over all weight vectors. And this also has a nice interpretation in statistical learning theory. So this averaging is one way of doing online to batch conversion. So online to batch conversion, I will talk about that also, means if you have this online algorithm and now you want to apply it to a finite test set, so what do you do? Which weight vector do you use? The last one, a random one? A better idea is to use the average one, right? Because now what you're doing is just prediction and not learning anymore. And averaging is, it has a status in learning theory. All right. So, should we make a break now? Yeah? Okay, good. So let's get started again. So the algorithms I talked about before, none of those algorithms actually took care of what I call maximizing the margin on the training data. Maximizing the margin on the training data is one of the concepts that has been introduced in the statistical learning theory community in order to make sure that you do a good job on your test data. This is what you are actually interested in. So if you look at these examples here, if you learn a decision boundary between positive and negative examples that looks like this, you're doing a good job on the training data, right? But you can imagine another decision boundary would maybe be better, one that would be right in the middle, that has the maximum distance between the next positive and the next, or the closest positive and the closest negative example. Why would that be? Because that learning to maximize the margin means that you have a confidence that you can apply to your unseen data. So you're not just running after every training example, but you classify the training example with the maximum possible confidence of classification. And this is what support vector machines are doing. And support vector machines have been all the rage in the 90s. They are still useful techniques if you have a feature vector of dense or sparse features. If you know what your features are, they are very efficient solvers for support vector machines. And what's really nice about them is there has been a lot of theoretical work on support vector machines that give you insights into techniques that are still useful for other types of models, like regularization and going from linear to nonlinear, and all of those techniques, they have been developed for support vector machines. And even if you don't like these models anymore, the techniques, they come from there, from that area, and you can understand what's going on if you look back to support vector machines. So maximizing the margin means we define the margin for our multi-class classification problem as the maximal distance between the score that you learn on your training example and all the other scores. So you want to differentiate the score. So you have a very high score for your training, for your positive example, and that should be higher than all the other examples. So the support, the perceptron does not take care of maximizing the margin at all. What it does is it learns, and we can show that the error of the perceptron is bounded by r squared divided by gamma squared. So if the margin would explicitly be optimized and made larger, then the error would be smaller for the learner. So what the support vector machine actually is, it's a perceptron that maximizes the margin explicitly, not just by hoping that it maximizes the margin. It does it explicitly. Otherwise, they are very much the same. So, so if we start out formalizing the objective for the support vector machine, so what I just said, we make this formal. We say we want to maximize the margin for a model that is defined by a weight vector W, which is set to 1. So the length of the is set to 1. Why is this? Because if we don't make this constraint, then you can find or optimize your problem trivially by scaling the weight vector, by just multiplying the weight vector by a certain constant. Then, as you can see, the margin will become larger, right? Multiplying this difference here by beta greater than 0, will also make the right-hand side larger. This is not what we want to do. This is why we have to make this constraint. Okay, so if you know about support vector machines, this is not the objective that you normally see in papers or that you see in implementations. So you have, from this intuition, you have to derive the objective and then do, again, unconstrained optimization to get to your algorithm. So how do we get from this form to the form that we can actually use for optimization? So what we do is, so I'm just rewriting what I had before here, maximize the margin for all training data. I'm just using, so I'm redefining the variables. So instead of W, I'm using U, and U is just a scaled version of W. And as we have seen before, scaling doesn't change the result. Yeah? If I use U or W, it doesn't make a difference. So if I define U like this, then I can say that gamma is 1 divided by the length of U, right? Because the length of U is defined by, is 1 divided by gamma if I satisfy the constraint above here. So I'm just doing this change of variables, and I'm using my new variables to reformulate the algorithm, and then what will come out is I will have a nicer form of the algorithm, the form that you normally see in papers and textbooks. So step 1 is I'm replacing gamma by 1 over U. Yeah. Then maximizing 1 over U is the same as minimizing U. Then I'm replacing the W here by gamma times U. Then I can see that I can cancel the gammas. And as a last step, what I'm doing is, since I have a minimization problem, I'm not minimizing U, but I'm minimizing 1/2 times U squared. This will be nice if I do. The only reason for doing this is when I do the derivation, As you can see, if I take the derivative of this, then it's 2 times 1/2, and it will cancel out, right? Okay, so this is the form that you have that you should be used to if you have seen support vector machines in textbooks. It says the margin has to be greater or equal to 1, and the reason why it's 1 here, it's just because it cancels out here. The only difference between the original formulation on the left-hand side and the right-hand side is instead of fixing the length of W, we are fixing the margin. So it's not that the margin has to be 1 and nothing else. It's the margin, we are still maximizing the margin. This is just what falls out if we do a change of variables, right? So and this is now the optimization problems we are looking at. This is minimizing the margin. This is equivalent to minimizing the margin. It's no longer that obvious. Here it's, maximizing the margin, that minimizing 1/2 times the square norm of u, that what does this have to do with maximizing the margin? Well, it's just the change of variables. This is it. And such that the distance of the gold standard label to all other labels is greater than 1, which is our fixed margin. So this is a constraint optimization problem. So as we had for naive Bayes, we have an objective and constraints. And what we can do is we can use either we can do the derivation with Lagrange multipliers, using Lagrange multipliers for each of those constraints. Then we end up with an objective that does not have a closed form solution. It becomes a quadratic program. And the first support vector machines solvers were actually, they used a standard off-the-shelf quadratic programming solvers to solve the problem for support vector machines. This was quite inefficient, and now there are techniques to do it better, and the techniques that do it better, what we do is we find a way of reformalizing this constraint optimization problem as an unconstrained optimization problem, and then we solve this unconstrained optimization problem directly. Okay, but first, in order to do this, what I had before on this slide is I'm making the same assumption as I did for the perceptron. I'm making the assumption that the training data are separable. What we can do is we can generalize the problem to the case where the data are not separable. What do we do there? We introduce what's called a slack variable. So what we are doing is we are saying our constraint can be violated by a certain amount, xi, which is greater or equal to 0. So if we basically overshoot or undershoot, then we account for this by xi, and we allow some kind of error, which is formalized by this term xi. And in the objective now, in this minimization problem, we have to maximize the margin and we have to minimize the error, right? And you can have a trade-off between minimizing the error and maximizing the margin by this variable c. So if you set c to, so how do you have to set c in order to maximize the error? Also, or put all the weight on minimizing the error and not maximizing the margin. So there could be examples where the training data are actually really nicely separable and I want to minimize the error. Then do you need a high C or a low C? High C, right? And if you are more interested in maximizing the margin, if you know my data are noisy and I want to make sure that I'm maximizing the margin and I'm allowing some errors on the training data because I will do better on the test data, then you have to set C less than 1/2, right? So this is a trade-off. This is one of the most important parameters in when you apply support vector machine. So every toolkit has this parameter. Might not be called C or whatever, but you have to know about your training data, and then you will do a good job by tuning this right. Okay. So this is the final form of the constraint optimization problem, and as I said, you can use quadratic programming solvers to solve the problem, but we can do better. So what we can do is we can get rid of these constraints by just folding the constraints into the objective. You can already see how it can be done, right? You are just solving this inequality for psi and then expressing psi in terms of the margin, and then you have an unconstrained optimization problem. So what we first do is, instead of what we had before, so we are pulling the 1 on the other side in order to solve for psi, yeah? Then we change the variable that we had up here, c, to lambda. So it doesn't matter where you have this constant that allows you to trade off between minimizing the error and maximizing the margin, either here or here. And this is nice because it allows you to see the support vector machine as an instance of a more general problem, like you have an objective and a regularizer. If you have the constant on the regularizer, this allows you to make the regularizer stronger or weaker. And then, so by looking at the properties of our error function, what we will see is that you can express this as the maximum of 0 and the negated error, because we just said that psi has to be greater or equal to 0, right? So we can maximize at 0, and this term here will be capped at 0 if the weight that you assign to the positive example is larger than the weight that you assign to all other examples, or to the example that has the maximum weight at a margin that is greater than 1, right? This is what this term here means. You have to make sure that you assign a high weight to the correct example that is higher than all the others, or it's higher than all the others if you assign it a higher weight than the maximum weighted example by a margin that is greater than 1. So if you do that, then you have no error. No error is accounted. So in this form of the loss function, so this is the final form here, is called the Hinge loss. And why is it called Hinge loss? Because the form of the loss, so I will have a slide later on that shows that it looks like this, right? That the error is capped at 0 and it grows linearly if there is an error accounted for. So it looks like a hinge of a door, right? But what we have is we have now an unconstrained optimization problem. We maximize this loss function as a function of W, and the loss function is this. This is our error term, and this is our regularizer. So, or basically, this is how we express our error, this psi, rewritten psi, and this is how to maximize the margin. Okay, and unconstrained optimization of this means just you have to take the derivative and plug it into a gradient descent or a stochastic gradient descent algorithm. Yeah, and we'll see quickly. So I have a few more slides on the objective before I show you how the algorithm works. So what we want to look at next now that we have seen naive Bayes, logistic regression, perceptron, and support vector machines, is a viewpoint that also comes from statistical learning that summarizes all the different algorithms as particular instances of a framework that takes an objective and regularization. And regularization is one of the key components of making sure that you are not just optimizing on the training data, but that you do a good job on test data. And the support vector machine is a very nice example of this, because the regularization term that support vector machines use falls out of the original objective. For the other algorithms, for the perceptron, you can tack on the regularization and see, if I do regularization for the perceptron, I'm getting actually to support vector machines. But you also can tack on the regularization to logistic regression or to naive Bayes. And then you have this general form of algorithms that minimize the error and regularization. And for the support vector machine, the regularization is equivalent to maximizing the margin. So we will first look at this general viewpoint, regularization, which allows us to recap all the algorithms. Then we look at learning techniques, online learning techniques that allow us to give more efficient algorithms for learning logistic regression and support vector machines, as more efficient than the quadratic programming solvers that have been used for a long time, or even more efficient than the gradient ascent that we have seen for logistic regression by doing online or stochastic gradient descent, which means that we're doing it example by example. And the perceptron is already an online learning algorithm. And then I will show you how to go from linear to nonlinear, but keep all the machinery of convex optimization. So regularization means, let's say we are doing regression. This is the points that we want to predict. So this is actually, this would be a good curve, a good fit. This one is not really a good fit, so it fits the training data perfectly, but as you can imagine on test data, well, if the next point is here and here, then they are not captured, right? This means high variance, so you're overfitting the training data. And high bias means you use a very simple model and you make sure that you are not learning too much, you're not tuning your model too much to the training data. So you have to find the right trade-off between bias and variance. And this is what you do by regularization. Regularization gives you a bias, avoids some variance, but you can't do too much regularization, because then you're not learning anything. So how is regularization? So this is a real example. So if the data points are close to each other, then yeah, you can have a good fit, but sometimes these spikes here, of course, they won't work well on unseen data. So overfitting is the problem of not having enough regularization, of having too much variance in your model, fitting the training data too well. And so what most of statistical learning theory was about is different ways of regularization from all different kinds of perspective, Bayesian, metrics, whatever. Just making sure that you have a regularizer that allows you to do good on unseen data, and inventing capacity metrics that tell you how good you actually do on this unseen data. And so it was yeah. I mean, statistical learning theory is really important, but at some point it became an industry of inventing capacity metrics. So every paper invented their own metrics and showed we are doing very nicely on unseen data under our metrics, and nothing became comparable anymore. So it's, but yeah, there are some insights in regularization. and we'll just cover it very superficially. So by saying overfitting means that there is, in your training data, you have some prominent examples, some prototypical examples, and what you don't want to do is not just learn weights or prefer the prototypical examples, but prefer every outlier. Basically learn everything that you have seen in your training data and not be able to adjust to a little bit different data that are your test data or your unseen data. So for example, if you do parsing on the Wall Street Journal, then you will only see the word fake as an adjective. But you can imagine that fake can also be used as a verb, and there's no chance if you use let's say text classification or parsing on the Wall Street Journal and your features are indicator features that you can ever figure out that it could be used in another meaning as well. So this is a really bad way of overfitting. So what you can do is you have to build models that allow more possibilities, richer models, and regularize them. Regularizing means you have a very expressive feature basis, but you make sure that the weights cannot grow too large or too small. So what you do, for example, by using a squared norm on your weight vector, means that if the W's grow very large in the negative direction or very large in the positive direction, then this is an indicator that you have captured an outlier in your training data. And if you make sure that in your objective, you also have to not only maximize the likelihood, but also make sure that this term here becomes small, then you're not allowed to have a large squared norm of the weights. This is a very simple intuition between what's going on. You're not allowing your weights to grow in directions that are not really representative. And for the support vector machines, we have seen that this squared norm of the weight vector actually was motivated by maximizing the margin, right? So the Hinge loss formulation corresponds to the margin maximization. We have our loss function and lambda times regularizer. And if we have lambda times regularizer as the squared norm, then we get back our Hinge loss objective. And we can take this to a higher level and use the same regularizer, because the intuition of regularization is just to make sure that the weights don't grow too large in either direction. We can apply it to logistic regression. So all we do is we change the loss function. So it's the same regularizer. Here we have the Hinge loss, and here we have the log loss. The log loss is the loss that we had this was our maximum likelihood for the conditional probability model for logistic regression. And you can use the same regularizer. So to summarize this, if you plot all of our loss functions as binary classification loss functions, then you can see that all of them are actually upper bounds on the 0-1 loss, which is a non-convex, non-differentiable function. And since we want to use convex optimization where we can take the derivatives, what we try to do is we try to define upper bounds when we do minimization that are convex and ideally differentiable in all places. So that function here is the perceptron loss. It's a convex function. It's just not differentiable here at the hinge. And the perceptron loss is very similar to the green one, which is the Hinge loss for the support vector machine. So I will show you shortly how the perceptron loss and the support vector machine are different. The loss functions are very similar. They're both Hinge loss type functions. Then the log loss, this red one, is what we had for logistic regression. And then there are different other variants where you have a squared Hinge loss or a modified Huber loss. So the difference of the losses is if you know something about your classification problem. So for example, if you know that it's a good idea as soon as you make an error to really penalize the model that makes an error very hard, then it's maybe a good idea to have a loss function that has a quadratic loss. So if you make an error, then it's huge, and if you don't make an error, it's zero. But sometimes it's maybe it's a better idea to have this exponential curve for the error. Sometimes it's nice to have this smooth degrading error. So it's not like zero and error, but something that is like inside the margin, right? So you're not doing it. You're doing the right job, but you're not doing the right job good enough. So this is basically a soft margin. So you can, depending on what problem you have, you can set up different loss functions and derive algorithms. So that's one view of what we have seen before. You're setting up different objective function, for example, an exponential loss function or log loss, it's called here, for the logistic regression model, and then you derive your algorithm by doing stochastic gradient descent or gradient descent. Or you set up a function where you want to have a linear growing error and you use the Hinge loss. Or where you don't, if you have an error function where you are not interested in a margin because your training data are separable at all times, then you can use the perceptron loss and derive the algorithms. So most of the algorithms were not developed in this way, but you can look at them at this way. Okay. Okay, online learning. So now we have seen how to make our models better by introducing regularization to make them work better on unseen data. Now online learning, this is all about how to make the algorithms better, more efficient and less memory intensive. And one can actually show, and I'm not showing this here, that this online learning scenario also has a positive effect on unseen data, because you have a bit of randomization in your algorithm, and randomization also avoids tuning your model too much to the training data if you have randomization in your algorithm. So online learning and batch learning. So batch learning is another name for what we had before when we talked about gradient ascent. So online learning, in difference to batch learning, is that for each example you do an update. Batch learning means you go over your training set and then you do an update after you have gone over your training set once. So if you have a decomposable loss function, then this going over the training set once and then doing an update mostly means you sum up the gradients for all your training data and average them, right? And for the online learning, you do an update one after the other. So the perceptron, as it was invented and as it's used, is already an online learning algorithm, because it looks at an example, makes a prediction, does an update. And the algorithms I've been talking about before, logistic regression, naive Bayes, and I didn't give an algorithm for SVMs, but I said you could use gradient ascent, they are batch learning algorithms. So again, batch gradient descent, this is what we had for logistic regression. You iterate over your until convergence, and what you do is you compute the gradient of your full training set. So you're summing up the gradients of the loss function for each of the training examples. And you can also average this, right? And stochastic gradient descent now means that, why is it called stochastic? Because the idea is that when you look at the training example one by one, you are choosing the training example stochastically, randomly. So the idea comes from you have an infinite sequence of training examples, and each of these each example you see is drawn from a distribution at random, and so this is a stochastic choice of this example. Or another way would be if you have a finite training set that you shuffle your training data, which also makes it random, or for a very large training set, you pick the examples from the training set one by one. So the proofs that you can give for convergence and so on, they depend on what kind of stochasticity you have with replacement, without replacement, and so on. But for us, we'll just talk about it in terms of online learning, right? One example after the other. And there has to be some randomness in the choice of examples. But the key is the difference between batch and online. So this is just an instance of online logistic regression where we replace this derivative by the derivative that we have seen for logistic regression for one example. But what I want to get is this here, I will go back to this. Online algorithms, what is the advantage of doing this? The advantage is the computational cost of one update, and this is what really is counted when you talk about how fast is my algorithm. Fast means how many updates does it need to arrive at the optimal value, to arrive at the global minimum if you have a convex function. So the computational cost for online algorithms is 1 over the size of the training set compared to batch. Yeah? So this means you're doing many more updates, and each update is less costly. So it's more, at least memory efficient. But the downside of online learning is that this stochasticity you are doing, so every update is really different from the update before, because you are doing an update on one example only. And the gradient from one example can vary radically from the gradient from the other example. And you're building one gradient on top of the other gradient. So you have high variance in your updates. And this might slow down convergence. And this is why if you use online learning, you have to have the learning rate that we had in the algorithms, this alpha. You have to have a decaying learning rate. So decaying means that if you have done many, many updates, then the learning rate becomes smaller and smaller, and the steps become smaller and smaller. So in the end, you are doing very small steps only. This is the only way to guarantee convergence. If you have a constant learning rate, then you can't guarantee convergence. For batch learning, you can use constant learning rates, which always make big steps. As this is because batch learning, because you're doing an average all the time over all training examples, this cancels out the variance and makes the learning rate or the convergence rate faster, even if the time to do an update is more time, it takes longer and uses more memory. So this is the trade-off between online learning and batch learning. But if nowadays, with very large data sets, big data sets, there is no way to do batch learning. You can't just wait until you to do an update until you have gone over 10 millions of parallel sentences in machine translation and then do an update. You have to do it example by example, otherwise you're not getting anywhere. So this is just, yeah. And the nice thing is there are ways to reduce the variance in online learning, and so you get the best of both worlds. Online learning that has its variance reduced and converges fast, and uses not a lot of memory. So again, what are the online learning algorithms? This would be online logistic regression by just plugging in the gradient of our logistic regression function evaluated at one example, xt, yt. Then online support vector machines. So this is if you want to re-implement a support vector machine, this is the algorithm. You just take this subgradient or gradient. Subgradient it's called because it's not differentiable at this at the cusp of the hinge, and we just set the gradient to 0 at this point, and this makes it a subgradient. So, but it's very simple to implement. You say the gradient is 0 if you don't make an error, and otherwise it's the gradient of my objective, namely the difference of the feature vectors, which is the very same update as the perceptron, and the only difference is in addition we have this regularization term, and the regularization term, the gradient is lambda times w. Yeah? 2 times lambda half of the squared norm is lambda times w. So if in your algorithm at each update you make this decision, error or not, update by changing the feature vectors and adding this regularization term, you have a very simple algorithm, an online version of the support vector machine. And how does the perceptron now relate to this? The perceptron is actually, it's the same objective, the same hinge loss objective as the support vector machine, just without regularization. So the objective just says, not the margin has to be 1, but the margin has to be 0. So we have to make the right classification. So this is how people later on rephrase the perceptron as a hinge loss optimizer, right? It's a hinge loss that is not, doesn't have a margin, but just the correct classification, and it does not use the regularizer, which is motivated by maximizing the margin in support vector machines. So, but if you start from the perceptron and add this margin of 1 and the regularizer, then you have an online version of the support vector machine. Okay, so now what I said about variance reduction. So one of the techniques for variance reduction that is used in every online learner nowadays, it's called the momentum technique. It's also from the 1960s. So if you look at our update here, so we update a learning rate in the direction, negative direction of the gradient, plus mu times velocity. And velocity is the difference of the weight at this step and the step before. So velocity tells us if the weight vector that we are looking at the moment is very different, does it point in the same direction or in a different direction from the weight vector from the step before. So if they point in different directions, then we will, since we are doing a minimization, we will basically pull back our step in the negative direction of the gradient by mu times velocity. So if we going in a different direction than before, we know, okay, this is maybe not a good idea. We don't want to destroy everything we have learned before, so we pull back a little bit. And if we go in the same direction, then this cancels out and we are doing the full gradient step. So and this momentum technique reduces variance greatly and allows you to use online learning, variance reduced, with fast convergence and very little memory requirements. So there are many refinements of this momentum technique, but this is the basic, and it's very easy to understand. All right. Then one one thing about online learning is, so online learning, it's not just, the idea of online learning, it really comes from this streaming scenarios where you have an infinite sequence of data coming in, and where you have to learn while you are doing predictions. This is why it's called online, right? And in our setup, we always have these finite data sets and training set, held out set, test set, and we loop over our finite training set. And so we have to ask the question, when we do our actual evaluation, our actual testing, how do we convert from online to batch? Which model do we use when we actually apply it to our unseen test data? So it's not given that you actually have to use the last weight vector and then do prediction using the last weight vector. Yeah? It could be a random choice. There are also theorems that show that a random choice is just good. Or what you normally do is you use the best model on a held out set under a particular task-driven metric, like for machine translation, you use maybe the model, the WT that gives you the best performance in terms of Bleu score on a held out set. And then you use that model to predict on the test set. So not a random one, not the last one, but the best under a certain metric. So if you want to have a formal way of choosing a model, then one way is actually the averaging idea. So the average perceptron, as I showed a few slides before, you can show for the average perceptron that the expected loss, so W with, I forgot how to call this, bar, yeah, W bar, basically the expected loss under the averaged model, you can show that the expected loss is always smaller than the loss you made during online training plus some term here. So there's a paper by Cesar Bianchi that shows that in online to batch conversion, you can give an estimate of the error that you will do on unseen data when you use your model as a batch model. And for the averaging model, this will be the error that you have seen before and some term that decreases with the number of iterations you're doing. So it's a well-defined standard way of doing average also online to batch conversion. So this average perceptron, it was invented without any theory, but there is a theory behind it. So it's a good way of doing it. Okay. So to summarize what we have seen before, so I talked about linear models and convex optimization. So the whole class is called linear learners, and it's a funny term because I don't want to call it linear models or linear optimization, because the optimization basically it's techniques for convex optimization that can be applied to linear models, which are convex models, right? So the models, all of the models are linear models, and we use the techniques of convex optimization to optimize the parameters of these linear models. And those two techniques together, the linear model and convex optimization, I call linear learners. Yeah? In some papers you find linear optimization, but to me, linear optimization sounds more like you use some linear programming solver toolkits, and this is not what we are doing. We are taking the derivatives and doing gradient descent, so it's quite different from standard linear programming. Then I talked about regularization, which means you are improving your models to do better on unseen data, and then online to batch learning, how to do your optimization better by doing more updates, and each update is less costly. Then the last part is nonlinear models, and So the nonlinear models I will talk about, they can still use convex optimization. So in difference to what you will learn in later classes, this is a different way of introducing nonlinearity is by changing the objective to be a nonlinear objective. What we are doing here is we are changing the objective, but we are not making the nonlinearity part of our optimization problem. So we use some ideas and tools to infuse nonlinearity into our model, but we are not optimizing the nonlinearity. And this allows us to work in nonlinear space without having all the problems of nonlinear or non-convex optimization, which means we don't know where the global minimum lies and which of the local minima is best and how to converge fast to this global minimum. Okay, so the nonlinear models I talk about are all nonlinear models. They are able to model decision boundaries that look like this in two-dimensional space. This was not a linear decision boundary. And the models are known as kernel machines. And kernel machines is convex optimization for nonlinear models. So what does it do? What do? We project a linear model into a higher dimensional nonlinear space. And we use some predefined operators for this projection. So we have some theorems on which operators are allowable, so which kernels work and which don't work. And then we can make sure that we can do nonlinear optimization or nonlinear learning with the same tools and the same guarantees that we had before for convex optimization. So one of the most well-known kernels is the polynomial kernel. So what the polynomial kernel does is, so a kernel always corresponds to a feature space. So a kernel is basically, it's an operator that implicitly pimps your feature space. Yeah? It makes your feature space richer and more expressive. And so the monomial feature space is basically, it takes the ordered monomial, it takes all possible products of your features, right? This is a nonlinear operation. And why does it make sense to take product of features? So for example, in natural language processing, a product feature means you make sure that this word and the other word in one feature have to be present. So it's this combination that you're looking at. And you assign one weight to this combination. Or in vision, when you do digit recognition, you want to differentiate a 0 from an 8. By the 8 has 2 zeros. And if you have a feature that knows that it's two zeros, then it's, you can differentiate the 8 from the 0. Otherwise, you would have, twice the 0, which is the same as the 0, just once. It's something, conceptually something completely different. So what the monomial feature space does is, by this ordered product, we can see that nonlinear mappings can be created for a lot of problems that are not separable or not solvable with the original non-product or non-extended feature space. So, an example would be a decision boundary like this here, where you can see in two-dimensional space there's no way that you find a line that differentiates the circles from the crosses. But if you use a feature map that adds a third dimension and takes let's say if you have only two features, takes the products of the first feature with itself, the second feature with itself, and the first with the second feature, then all the feature weights inside this circle here, let's say they have a distance of less than 1, they lie behind this hyperplane, and all the others become much larger and lie above this hyperplane, and then in this three-dimensional space you can differentiate the positive and the negative examples. All of a sudden you can find a linear separator that you couldn't find before. So in this higher dimensional feature space, things are possible that have not been before. And the monomial feature space is just one way of many problems can be solved with this. So for example, this famous XOR problem, it looks exactly like this here. The exclusive OR problem in logics, this has been the reason why perceptrons have been dissed, and then people invented the multi-layer perceptron, which could solve this problem, but you can solve the same problem with monomial features as well. So if that were all, then kernels wouldn't be that interesting. If you would always have to create a higher dimensional feature space, because that's costly, right? I mean, if you do computations in this higher dimensional feature space, then yeah, every computation becomes more inefficient, more costly. So what you do is in kernels, you want to define an operator on dot products. So you have to find a way of formalizing or rewriting your algorithm so that it has at some point a comparison of examples. So a simple comparison or similarity between examples is the dot product in feature space. And then on this dot product, you can generalize the dot product so that implicitly by this generalized dot product, you're doing an expansion of your feature space. So if we go the other way around, if we start from the monomial features and we look at the dot product between example x and x prime, and we unfold each of the features. So we take the square of the first feature, of the second features, of the first and second, second and first. Then we see that in the end, what we get is x, the dot product of x and x prime squared, yeah, by a monomial feature map of order 2. So and this can be generalized for the polynomial kernel in that way that, that we can say for every kernel that we apply to a dot product of two examples, there is an implicit feature map that maps to a d-dimensional extension of the feature space in this monomial feature map. So, and the key idea of kernels now is yeah, it's expressed in this theorem here. If we have a particular definition of kernel, then every kernel implicitly defines a feature map and an extension of a feature map. So that means that we don't actually have to know about the feature map anymore. If we formalize our algorithm in a way that it includes these dot products between examples, and we replace the dot product by something like a dot product that is a kernel, which is it's just another way of doing by using appropriate kernels that follow the definition of kernels, like a kernel has to be symmetric and positive definite. So symmetric is clear, positive definite just means that on the diagonal you have to check that the diagonal values on this matrix are greater or equal to 0. For any such kernel, you can be sure that there is implicitly a feature map, an enriched feature map that allows you to do things that you couldn't do before. Like this map here. Yeah. So again, the kernel trick, sometimes you find this wording, kernel trick. So you define a kernel that satisfies these conditions, and you replace the dot product in your algorithm by this kernel computation or this kernel calculation. And then you can be sure that you have enriched your feature space into a higher dimensional feature space, and in many cases you can solve problems that you couldn't solve before with the linear model because you're now implicitly in a nonlinear feature space. So if we now apply this to the perceptron, you have to be clear that our features are over pairs. So our feature, also our kernel map is also over pairs. So we compare xt, yt to xr, yr. Can be the same x, but doesn't have to be. So if we now show how to kernelize the perceptron, so this is our simple perceptron algorithm where the updates look like this. If we make a mistake, what we do is we add the feature representation of the gold standard example and subtract the feature representation of the mistaken example, of the wrongly predicted example. So what we are basically doing is in kernelizing this model, we try to get rid of the weight vector. So we try to express the weight vector by comparisons between examples. So you can do this all more formally, much more formally, by doing Lagrange multipliers and comparing the primal problem to the dual problem, but this is an intuitive way of doing it, right? But it arrives at the same result. So the result is we basically want to find the dual of the weight vector, and the dual of the weight vector means expressing the weight vectors by kernels, by comparison between examples. And what we can see here in the algorithm is that one way of expressing the weight vector in a different kind of way is if we could see how to do this by just looking at the feature representations. The weight vector, if we start at 0, it's just it's adding up and subtracting feature representations, right? The good ones and subtracting the bad ones. And we are adding up the good ones proportional to the number of time we are making a mistake and doing a misprediction. Then we are adding up a good one and subtracting a bad one, right? So alpha could be our new parameter to optimize that tells us the proportion of times the label has been predicted and caused an update because of misclassification. So we can express the weight vector basically as the sum over all examples and updates where we made a misclassification, where we add up the good one, subtract the bad one, alpha times. So we now got rid of W in our algorithm. And then if we want to use this, so what we do is we just rewrite our prediction function by replacing W by this function that we have just defined before. So W is now rewritten as the sum over feature additions and subtractions times alpha. And we have to take the dot product of W and phi, the feature representation for the unseen example. And this is where nicely our comparison between examples comes into the algorithm, right? So we have to compare the good example to the new one and the mispredicted example to the new one. And we see we have a dot product here and a dot product here, and we can replace this dot product by a kernel. and all of a sudden we have a perceptron algorithm that uses not weights, not the primal representation of weights times features, but a dual representation where the weight is expressed by the number of times I basically prefer, also have a closer similarity of my example to the gold standard example and a smaller similarity to the mispredicted example. Yeah? If I do prediction with this here, I have to make sure in order to maximize this that in order to get a good weight for an example, the example has to be close to the gold standard and not so close to all the other examples, right? And it has to have an high alpha. So the weighting of the kernel. So this is basically a way of rewriting the perceptron, and using the kernel here is a way of making the perceptron richer. And we can see it's a very simple algorithm. So we didn't change basically anything in the algorithm, right? If this kernel computation can be done efficiently, then we have a richer algorithm at no cost. So of course that's a lie. There is a cost. So kernel computations can be expensive because if you have a very large training set, then you have to compare this example to all examples in your training data. Yeah? And this can be very costly. If you have a very large training set, then it's a huge matrix that you have to compute. And luckily, there are other ways of doing this by explicitly constructing feature maps, and there has been in the 2010s, there has been a lot of work on learning kernels from data, and some of these works basically learned the feature maps and some learned the kernels, so it's two sides of the same problem, and learning kernels from data basically is the same as learning a neural network, right? You learn this nonlinearity from data, and the same people who in the 2010s worked on these learning kernels are now the people who work on neural networks. So it was a gradual shift from kernels that are predefined, that allow you to do convex optimization, to learning the kernels and still staying in the framework of convex optimization, to just getting rid of it and learning everything in one big approach. Okay, so to summarize kernels, so if you have predefined kernels, either you have a good idea how to define them, or you learn them separately and then use them. They allow you to project your feature space into higher dimensions. And you can make nonlinear problems solvable that have not been solvable before with your standard linear model and feature representation. But the disadvantage, so kernels depend polynomial on the number of training examples, right? So there are certain ways, also quick and dirty ways to get rid of this problem. So for example, you could imagine that you sample training examples and you compute the kernel only on randomly selected training examples, which is one way of doing it. But another and better way is to learn the feature map directly. So this is a very nice paper by Rahimi and Recht. So what they call it randomized feature maps, or random kitchen sink feature maps. So what they do is they basically build up a one hidden layer neural network, and the nonlinearity comes in this first layer where they have, so they use it for acoustics, for speech recognition. They use a random binning or random Fourier transformation of their features. So random doesn't mean it's completely random. It means you have a certain size of bins that you can change, right? So every data point still falls into its correct bin, but you can randomize the size of the bins. Or when you do a Fourier transformation, which corresponds to representing different spectra, you can choose which ones you want to choose in your representation. All of them, or just the red, green, blue ones, I don't know. So and this randomization gives you the nonlinearity, and then all you have to do is you have to optimize the weights from the hidden layer to the output layer, and you can use a convex optimization model for this. And this they showed in this paper that I'm citing in the paper section, that this works just as well as neural networks, yeah, because it is a neural network, yeah. And the problem is simple enough, but of course you have to know something about this feature representation. And if you work on speech data, then basically you have to choose this randomization properly, a Fourier transformation or binning. Not everything will do. So you have to have some prior knowledge in order to get this to work. But still, you have all the advantages of convex optimization. All right. That's good, right? 10 more minutes, right? Yeah, I'm done early. Yeah, that's fine. Okay. Yeah. Okay. To summarize, so basically, what I showed you today is basic principles of machine learning. One way of viewing it is first you analyze your problem, you set up an objective function that has the properties that you want to express, and it's amenable for ideally convex optimization, right? So it's a function that is convex and is differentiable. Then you can use these very efficient stochastic gradient descent algorithms. And you can do it in batch or online, depending on what your data set looks like. Batch learning converges faster in theory, but it uses more memory. Online learning, if you have large data set, is probably the way to go. Then what model to use? Well, I just talked about linear models, and out of the linear models, the choice between perceptron, logistic regression, naive Bayes, support vector machine also depends on how noisy are your data. Are they separable or not? Do you need regularization or not? Do you just want to count, or can you run an iterative algorithm? Are you interested in turning your model around and simulating? So you want to have a joint model, or do you want to just do multi-class classification? So I can't answer that. So you have to figure out yourself what's the best model. And one last word on how this is useful for the classes that are coming up. So the multi-class linear models, as I presented them, are the building blocks for structural prediction. So where, as I said, the outputs are not just classes, they are structured outputs, like parsers, translations, sequences, but they really build on the same techniques that we have seen here. Then for graphical models and for neural networks. So the multi-layer perceptron is just stacking on perceptrons onto each other. So the outputs of different perceptrons are taken as features for the next layer. And this makes the whole enterprise go nonlinear and non-convex. But you can do the same as with some of the kernels we have shown. So again, to make, I mean, I'm using neural networks as well, but I have to make a case for the kernel machines because they are not really dead. I mean, you should know about it and not just forget about 20 years of hard work. Yeah. So kernel machines allow you to do convex optimization and still go nonlinear. by not using the nonlinearity in as part of the optimization problem. It's just a given, or you learn it separately, and then you plug it in and you stay in the framework of convex optimization. Neural networks, they learn the combinations of features, so it's not you define a polynomial kernel that takes the products, which products to take, and the order of the products. It's learned in the neural networks. And so basically similarities and nonlinear combinations can be seen as being learned automatically because all possibilities are possible, are in there in the neural network, and some of them are more important, some of them are less important. You learn it automatically. But you are going into you're leaving the framework of convex optimization, and things still seem to work, but they are poorly understood. So it's not clear why the local minima are all the same and which local minima are to prefer if you have a way of preferring one over the other. So I'm not saying it's not the right way to do, but it's if you're interested in theory, if you're interested in convergence proofs, convergence rates, then you have a hard time if you want to do that for neural networks, because they seem to work and people don't really know why. So if you don't care, fine. Yeah. Thank you very much. Questions, please.
So what do you recommend in order to perform hyperparameters optimization? Because, well, when we use a kernel, for example, we use exponents and calibers with SVM, this kind of stuff. So it's really difficult to optimize it.
So meta parameters, you mean like the regularization constant, and yeah. So I would recommend to use reinforcement learning to do that. So there are ways of using reinforcement learning if you have a small set of meta parameters and you have your task, and the task gives you a response which parameter setting is best. And so it's basically an automatic way of doing the grid search that you normally do on a held out set by just letting your system run with a particular meta parameter setting, getting the task-based performance, and then using this feedback to retune the meta parameters. So there are some papers that you can easily find on arXiv how to use reinforcement learning. And everything that works for neural networks, of course, works for linear models as well, right? They are just simpler versions. Yeah.
Hi, Stefan, and thanks for an interesting talk. I have a very generic question about kernel selection. So I'm assuming that one would rely on one's understanding of the data set in terms of selecting a specific kernel. So what thoughts do you have on kernel selection if you don't really know much about the properties of the data set you're looking at?
You should always first get to know your data set before you ask a question like that. You have to do some, so this is where descriptive statistics or exploratory data analysis comes in, and there are textbooks on that, and you can do your linear regression is a really good model to find out about separability of your data set. This will give you a hint if you actually need a kernel or not, and then you can do correlation analysis on your features, and if you don't do that, you can't answer questions like that. You can't just, or you take a toolkit and you just try out this kernel, the other kernel, the next kernel, but that's not the proper way to do it. Unfortunately, in most computer science programs, descriptive statistics, exploratory data analysis is not really taught as well. So let me ask a question. Who knows about linear mixed effect models? Who uses them? Yeah, but the majority of people have never heard about it. When they analyze their data, they take the result on the test set as at face value. So nobody cares about random effects and things like that. So this is part of how to analyze data, and not just analyze the results, but analyze the data you have in front of you, and then you can choose the right model.
If I may just ask very briefly, from a data pre-processing perspective, things like taking outer products of your columns, of your features, does that help in terms of getting a kernel to provide better results?
That would be one way of trying out what the properties are. I mean, you can do standardization by subtracting the mean, dividing by the variance, and see if that helps. And you can do making all behave like bound them into a space between 0 and 1 by using a sigmoid or a linear transform. But you have to try it. You have to try it on your data set. There's no one recipe that works for all cases. So it's.
Thank you.
I have just a follow-up question on this question of where you said you should look at your data. But if you look at your data and you actually get some information about it and can then decide which algorithm to use, that would be essentially something that can be learned by a model, right? So, and I think there have been attempts to do something like meta learning in the past, and they've all failed. So, is there actually some reliable literature on how to really apply the insights from descriptive statistics and other kinds of statistical analysis of your data in order to choose the model? Because
I mean, for example, you can figure out by descriptive statistics, and some people recommend linear regression as a tool of descriptive statistics in order to find out about the separability of data. If you need techniques that make your model go nonlinear. For example, we talked about this iris data set, and the reason this data set was set up is in order to make sure that one of the classes is not linearly separable from the others. That's the only reason why they had this data set. And if you analyze the data and you see that, then you can make sure I need something that accounts for this non-separability.
But then it should be trivial to have a meta model for that, right? That does it for you. You don't even have to look at it. You just run your meta model on that, and the algorithm decides which algorithm to use.
Right? Maybe you could invent a meta model that tunes the parameters of your neural network, tunes the meta parameters, and figures out about separability in one go. Yeah, nice. Yeah, you could do it. Yeah, yeah. I think it's hard. Yeah, it's too many choices. Yeah.
Hi, here.
Yeah.
You mentioned something about now that we have large data sets, we shouldn't use the batch learning. But for example, I've been using TensorFlow recently, and it seems like they divide, or they suggest to divide in several batches, the large data set. And it seems like the update for per batch or by batch is working. Does that make any sense?
No, that's something different. So what they do is mini batching. So mini batching, it means the whole data set is divided up in small batches, and you're doing, to get, this is another way of getting rid of variance by averaging over these small, like say 100 examples. But you can never use the millions of examples in one batch. Mm-hmm. So mini batching is I should have mentioned it. That's right. Yeah.
Okay. Thanks.
So the reason I didn't mention it because I'm actually working on real online problems where you don't have a mini batch. So I'm actually working on problems where you get the feedback example by example, so bandit learning, yeah. And you can't think about mini batching in that scenario. You make a prediction, get a feedback, and you have to update. And so this is why I really am interested in this online scenario. But it's right, yeah. Mini batching is a good way.
So how is it different from stochastic batching?
Online and stochastic is, some people use it exchangeably, but some people make the difference that stochastic means you're making an assumption on the distribution that selects your example in the sequence. And online doesn't make necessarily this assumption, so the example could be chosen by an adversary. So if you think about game playing, so every time you make an update, the adversary chooses an example that is most dissimilar from the example that you have just seen. So an example that is really hard, an example that is just the opposite of what you have just done before. If you do a game move, then this move is just not right for the next example. Yeah? This is stochastic versus online, but they both look at example by example updates. Yeah.
In a nonlinear data set, if you have a problem of sparsity, how do you deal with that when you do the predictions and you use the current trick? Because sparsity is generally a problem, and then normally I think of reducing the dimensions. So in this case, we're saying that we are projecting into higher dimensions, and how do we deal with it?
You can also use kernels that reduce the dimension. It's the same techniques that do projection into higher dimensions or lower dimensions. It's depending on what the problem is. What the problem is, you can use a kernel that does dimensionality reduction. So again, you have to know about your data set, and yeah, you have to know about your feature set. Yeah. So if there are no more questions, so what you should look at is this last example I gave with this randomized feature map. So if you think kernels are old-fashioned, I don't want to bother about this stuff, then this randomized feature map, this is basically a way of using kernels and still staying modern, right? Yeah. And it works very nicely, and there are some ways of getting, without a whole lot of metaparameter tuning, getting the same results as with having a neural network run for weeks and doing metaparameter tuning. So that's a nice setup. Yeah.
Sorry, one last question. So what would be a good way to deal with class imbalance?
Class imbalance. So for example, for support vector machines, there have been ways of, so basically what I showed you before with this C parameter that trades off the error minimization and the maximization of the margin, you can do that for each, you can introduce a parameter for each class. So how important is each class depending on how many data you see for this class or for the other class, and you can do it for the margin and for the error minimization separately. So they are called, I think, actually, I'm not sure if they're called imbalanced, but something like that. So I forgot the actual name that people use for that area. But you can build it directly into the objective. Nah. I forgot, I don't know. So what I wanted to show you also is on the slides, I have some papers that might be interesting. So the first one is this paper on the frog example that talks about the cognition of the frog. So the people on the paper are actually biologists, and the second one, he founded a whole philosophical direction called the constructivism. So he basically, on his knowledge from biology, he wants to make the point that everything is constructed, right? Not just the frog constructs his world, we construct our world. And so there is no truth and nothing that is really touchable, right? It's all just social norms, and so it's quite interesting. But anyway, so this paper is, I think it's a good start to show that what we are doing, it's not more intelligent than building a model of the frog's cognition. It's just building a model of a text classifier's cognition, which is not much harder than dividing between edible and non-edible objects. Anyway, then a paper on naive Bayes, why it's still a good model. And the first author is Pedro Domingos, who maybe some of you know, as now he is famous for his predictions on the elections. So he was the only one, he claims, who had predicted that Trump will win the election. Then there are some papers on logistic regression and on the perceptron. So the Novikov paper, it's a really nice read that gives the original proof of the perceptron. Then on the support vector machine, the paper to read is the last one. It's called Training a Support Vector Machine in the Primer. So that's basically the algorithm that everybody's using now. So reformalizing the support vector machine as a Hinge loss and doing primal optimization. Then on kernels, that's the paper here, random features for large-scale kernel machines. And yeah, for optimization, there are the standard textbooks, but what I just came out last year, the paper that if you want to read about optimization is the last paper here by Léon Boutou, Optimization Methods for Large-Scale Machine Learning. It's a 100-page script on that tells you everything about online optimization for convex and non-convex objectives, and so it focuses on stochastic optimization, but it gives all the ingredients and the proofs, and you can really understand what, if you read this algorithm has a convergence rate of this and that, what this means and how you get there and what's important to get a fast algorithm. Yeah. More questions?
Maybe one last question. Yeah. It's at the bottom part. Yeah. No more batteries? You will have to speak louder, sorry.
Thank you for the talk. Actually, I wanted to just ask a question. While dealing with the streaming data and using online learning, what would be a good approach to choose what is the good data to adapt the parameters? I think that some of the streaming data that are coming may be not very good to use. Maybe they are outliers or something like that. Is there any good criteria to decide what is the data that how we should update the parameters?
So the standard applications of online learning to streaming data I know about is online advertising. And for online advertising, there's no choice. Basically, what you're learning from is the click of the user on an ad that has been displayed. And you have to use all of this information. You can't throw away any of it. And the applications I'm looking at is I want to do bandit learning for machine translation. So basically learn a machine translation model, not from gold standard translations, but from the feedback of the user who uses the translation. And one good way of doing it in this scenario is not to use the user feedback directly, but use the user feedback to learn a model that predicts, a feedback model, and then use the feedback model as your actual feedback to update the machine translation model. And in the feedback model, you can take care of what is an outlier, what is not an outlier. So because you have separated the problem of using the data, the streaming data, and learning from the feedback in the data. So that would maybe be a good way, and it's also done in reinforcement learning. So that's the area where we have to all look at now. Yeah. So there's no reinforcement learning class in this summer school. Next year there will be one, I'm sure. Yeah. Yeah. Yeah.
Thank you very much.